right, now we go to a very important theorem. Anytime you see the word fundamental in the title of a theorem, you got to figure it's a pretty important theorem. This is by Carl Friedrich Gauss, the prince of mathematics. The fundamental theorem of algebra had several corollaries, of which we're going to mention one. Corollaries are proofs off of the main proof. This says if f is a polynomial of degree greater than or equal to 1, then with complex coefficients, notice it's not real coefficients, it can be imaginary numbers as well, then f of x has at least one complex zero. So if the degree is greater than or equal to 1, there's at least one complex zero. Now if you think about this, if we have a zero, we have a linear factor of the polynomial, and based on the degree we can have up to n linear factors. So from this very important theorem, we come down to here. This statement says that the number of zeros of a polynomial, if f is a polynomial of degree greater than or equal to 1, with complex coefficients, right off of that, and f has exactly n complex zeros provided that each zero is counted by its multiplicity. So I mentioned this in some of the other problems. Oh, this one is degree 4, so we should have 4 zeros. This is the guy I was referring to. F is a polynomial of degree greater than or equal to 1, n greater than or equal to 1, with complex coefficients, and f has exactly n complex zeros. Now, sometimes the zeros are repeated, so you count the repetitions based on the multiplicity of the particular zero. And something that's kind of nice that with respect to imaginary zeros is the conjugate zero theorem. It says f is a polynomial, but this time with real coefficients. And if a plus bi, b not equal to 0, so an imaginary number, is a zero of f, then so is its conjugate, a minus bi, is also a zero of f of x. So that tells me, that's kind of nice, because if I know 3 plus 4i is a 0, then 3 minus 4i also has to be a 0. So that gets us over here to this example. It says, given f of x is x to the 4th minus 2x to the 3rd plus 28x squared minus 4x plus 52, and that 1 plus 5i is a 0 of f. Where to find the zeros? Well, look, degree 4, 4 zeros. I have real coefficients, and I have 1 plus 5i is a 0, which means 1 minus 5i is a 0 from the conjugate zero theorem. So how do I find the remaining two? Well, it's time to get some synthetic division going here. So I'm going to go 1, well, let's see if I can scoot this over just a little bit. 1, negative 2, 28, negative 4, 52. It's very convenient when they're in descending order, no missing terms. And I have 1 plus 5i. I'll start with that one. So that's 1. That would be 1 plus 5i. So if I add, that's negative 2. Negative 1 plus 5i. And then I have to multiply 1 plus 5i times negative 1 plus 5i. And believe it or not, these two guys here, you can kind of do the difference of squares. That's going to be 25i squared minus 1, so that'd be negative 25 minus 1. That would be negative 26. Multiply those together if you're not sure. FOIL. And that's going to give me 2. Then I multiply and I have 2 plus 10i. And I add and I get negative 2 plus 10i. And now I have to multiply 1 plus 5i times negative 2 plus 10i. And which is the same as 2 times negative 1 plus 5i, which is negative 26. This is going to be negative 52. And again, I can see that this is a multiple of what I just multiplied by, 1 plus 5i, or excuse me, negative 1 plus 5i. This is a multiple of it, 2 times that. So if I factored out the 2, multiplied the negative 1 plus 5i times 1 plus 5i, that's negative 26 times the 2 I factored out. And that gives me 0, which makes sense because it said that 1 plus 5i is a 0. Now, how do I get to the other two? I still have a cubic here. Well, I'm going to take the depressed polynomial. 1, negative 1 plus 5i, lots of algebra. 2, negative 2 plus 10i. Because remember, this is your remainder. And I'm going to divide by the other root that I know is in there, 1 minus 5i. All right, here we go. Bring the 1 down and multiply. 1 minus 5i times 1 is 1 minus 5i. Well, that one's nice. That gives me 0. 1 minus 5i times 0 is 0. Bring down the 2. 1 minus 5i times 2 is 2 minus 10i. Oh, really nice. And I get a remainder of 0. But look at my depressed polynomial that remains. My constant term, my x squared term. This gives me x squared plus 2. Well, I have my other two zeros. Because if I set this equal to 0 and I solve, I'll get x equals plus or minus, subtract 2 from both sides, the square root of negative 2, which is plus or minus I square roots of 2. So I have 4 zeros, and they're all imaginary. 1 plus 5i, 1 minus 5i. Positive, plus I squared root of 2 minus I squared root of 2. Okay? And these guys are conjugates because their real part could be like thought of as a 0. So find the zeros. My zeros are 1 plus or minus 5i and plus or minus I square roots of 2. That's some work. Here we go. Good problem. Makes you feel alive. Now, factor f of x as a product of linear factors. Well, that goes back to these guys. F of x is equal to this. These are my zeros, so I would have, you ready? X minus 1 plus 5i. X minus 1 minus 5i. X minus I squared to 2. And x minus a negative, or x plus I square roots of 2. Good Lord, look at that. Now I could simplify these two expressions here by writing this as x minus 1 minus 5i, x minus 1 plus 5i, and then these, of course, x minus I square root of 2, x plus I square root of 2. And that would be the linear factors. Solve the equation. Well, this is the same equation here. This is the same polynomial set equal to 0. So the zeros of this polynomial are the solutions to this polynomial equation. So what are the solutions? X equals 1 plus or minus 5i plus or minus I squared root of 2. Or if you write it as a solution set, 1 plus or minus 5i plus or minus I square root of 2 as my solution set. That's a good problem. Now the one below is a little different here. It says find a third degree polynomial f with integral coefficients, and the zeros are 2 plus I don't know if you can see this very well, 2 plus I and 4/3. Well, if it's a third degree or a cubic polynomial, this is only 2 zeros, this is a third zero, and we go back to the conjugate zero theorem. If 2 plus I, then 2 minus I as well, because we're looking at integral coefficients, which are real numbers. So what I'm going to do here is kind of what I did here. I'm going to write them out as linear factors, and then I'm going to have to, unfortunately, I'm going to have to do some multiplication. So my, let's call them f here, of x, would be equal to, let's use a bracket for right now, x minus, I have 2 plus I, x minus, I have 2 minus I, and here I have x minus 4/3. Now I'm going to have to do something with that. I guess I could use parentheses there. I'm going to have to do something with that because I want integer coefficients, I don't want any fractions. So I am going to multiply these together first. Now this is x minus 2 minus I times x minus 2 plus I, and then this is x minus 4/3. Once I get to that, I'll figure out. In fact, to make life a little bit easier, what if I just go ahead, because I can multiply by a constant and not change my zeros here, I'll just go ahead and put a 3 in here to get rid of that fraction. So I'm going to multiply the 3 times the x minus 4/3, that would be 3x minus 4. This times this. Now, I got to multiply these guys. This is going to take 9 little multiplications here. So I'm going to have x squared minus 2x plus ix minus 2x minus 2i minus ix plus 2i minus I squared, which would be minus a negative 1 would be plus 1. So I have 3x minus 4 times, let's see what I have here. I have an x squared. And let me just kind of cross them out as I go. I have minus 4x. Oh, hang on a second. These are like terms. But look what I have here. I have a plus ix and a minus ix. Those are gone. I have a minus 2i and a plus 2i. Those are gone. Plus 1. Nice. So I have minus 4x plus 1. And then if I multiply this mess out all together here, that's going to give me the polynomial I'm looking for. So here we go. 3x to the third, distributing twice, minus 12x squared plus 3x minus 4x squared plus 16x minus 4. So f of x, yikes, is equal to 3x to the third power. A minus 12x, a minus 12x squared, a minus 4x is a minus 16x squared. Plus 3x plus 16x is plus 19x, and then a minus 4. And unless I did something silly along the line, you know, signs or combining like terms or something like that, I think I got it there. That had a lot of work in it as well, but most of it was not new stuff. Most of it was just multiplying it all out there, and that of course is just algebra we learned back in our algebra days in high school. So let's finish this last example here. It says find a polynomial of lowest degree with zeros of negative 3. Now there's two of them, that stands for multiplicity. So there's two negative 3's and 5, and there are two of those. And we have to satisfy the condition that g of 0 is equal to 450. Remember back here where I popped the 3 in here? Because I didn't want any fractions? Well, instead of a 3, this time I'm going to throw an a in there. So bring it on up to here for b, the solution. And I'm going to have, this is g of x is equal to, I'm going to use an a, just some value here, variable representing a constant. And I'm going to have two factors of x, or of negative 3. So that would be x minus a negative 3 is x plus 3. I'll have two of those. And positive 5, so I'll have two of those. And on top of it, it says g of 0 is 450. That's to find a. So g of 0 is 450. So that's a times the quantity, 0 plus 3 quantity squared, 0 minus 5 quantity squared, and we know that equals 450. So this is a times 9 times 25 is equal to 450. I have 225a is equal to 450. I have a is equal to 2. Plug them right into there. G of x is equal to 2 times the quantity x plus 3 quantity squared times the quantity x minus 5 quantity squared. Now, here's the bad news. If you go to look in, like, let's say, in the back of the book, if it's an odd number problem, they're not going to have this. They're going to take the time to multiply all this out. X plus 3 times x plus 3, x minus 5 times x minus 5. Here, I'll do it in my head. If you believe this. 2x to the fourth minus 8x to the third minus 52x squared plus 120x plus 450. It's amazing that I have that ability to do that all in my head. And that is the solution. The third degree polynomial with integral coefficients. Oh, excuse me, wrong one. The polynomial g of lowest degree with zeros of negative 3 and 5, both with multiplicity 2, satisfying the condition g of 0 equals 450. You can see the lowest degree in this case, because we had 4 zeros, is degree 4.